Northwest 2021 Trial Paper 1. Question 9. A battery with an EMF of 14 volts and unknown internal resistance R is connected in a circuit as shown below. Now we see the circuit, and then we see that we have a battery, an ammeter, and then we have two resistors in parallel. There's a switch that between this resistor, that's 8 ohm, and then this point here, there's a switch there, and then we see a 3.6 ohm resistor in series with this parallel section, and then we see the internal resistance of the battery, and then the EMF. So when the switch S is open, the ammeter reading is 1.4 amperes. Now what we have to look for is which components are working with the switch S open. Now the internal resistance is working because the current is there. Current is inside the battery, then current is moving through the ammeter. Now current cannot go through the switch because it's open, so the current is passing through the 6 ohm and then the 3.6 ohm resistor. So this 1, 2, 3 components are working with the switch open. So the total current will be affected by the three resistors. 9.1.1. Calculate the total resistance of the circuit when the switch S is open. Now what we need to take note is, and be careful about, is not to see this as total external resistance. The question says calculate the total resistance, which means you have to find the total of this 6 ohm, the 3.6 ohm, and then the internal resistance, because these are the working resistors which are on the path of the current with the switch open. Unfortunately, we cannot simply add the 3 because the internal resistance is not known. So what we have to do is we resort to the second approach, which is the use of Ohm's law. And then we say that the resistance, that is R, is equal to the total voltage over the total current of the circuit. Since we know the total voltage, which is the EMF, and then the total current, which is the current measured by the ammeter A. So when we do that, we can say that 9.1.1, the total resistance of the circuit is equal to the total voltage divided by the total current, which is 14 divided by 1.4, and then when we evaluate that, we get 10 ohms. And then we look at the next question, which is 9.1.2. It says calculate the internal resistance R of the battery. So now we have the external resistance of 6 plus 3,6, which is 9,6, with the switch still open. The switch is still open now because we have not been told that it has been closed. So we see that one, and then we have the internal resistance R, and then we can use the EMF formula to find the total resistance of the circuit. So let us check what is there. The EMF formula, that is EMF E is equal to the total current times the sum of the internal and then the external resistance of the circuit. So when we write this formula, 9.1.2, we say the EMF is equal to the total current plus multiplied by the sum of the internal and external resistors. And then when we plug in the values, the EMF is 14, the current through the ammeter is 1.4, the total external is 9.6. Then we have the internal resistance at the unknown as the only unknown variable, and then that gives us a value of 0.4 amperes. Then we go to the next question, that's 9.1.3, which says that we should calculate the energy dissipated at the 6 ohm resistor in 3 minutes. Here we are giving some information, and the information is the resistance of the resistor is given, the time is given. Then what other information do we have about that resistor? We know the current that is going through it because the switch is still open. So with the switch open, the ammeter is still reading 1.4 amperes, which is the current that is going through the 6 ohm resistor. Let's remember that these two resistors do not share current. They are in series. They do not share current. They don't divide the current. So we use this information, the current, the resistance, and then the time, and then the work done or the energy dissipated, and then we select an appropriate formula. So when we go to the formula sheet, we see that the formula that connects these three variables is W is equal to I square R times the time. And then when we calculate that, we see that our work done, W, is equal to I square R delta T. And then we plug in the values of the current and then the resistance. And then remember that the time is 3 minutes. But we have to convert 3 minutes to seconds by multiplying by 60. And that is why we see that the time is 3 times 60. And then when we evaluate this with a calculator, we get 2116.8 joules. Then we go to the next question. That is question number 9.2. And then the information that we have there is that now the switch is closed, and we have to calculate the current through this 8 ohm resistor. That is this one. So this time this switch is now closed like this, and then the current is now using this route. So we have a parallel section that is not working, and we know that when resistors are in parallel, the total resistance is always less than the smallest of them. So our total resistance will be less than 6. And then as a result, what happens? The current increases. The current increases. So the current is no longer through A1, is no longer going to be 1.4 amperes, but is a different value. Now, we should be careful that we don't use this 1.4 in this calculation. We should not use a 1.4 in this calculation because the 1.4 is no longer the current that is read by this ammeter. Then the plan of this question is, this is a local resistor, the 8 ohm. So one method is to find the voltage of the parallel section, and then when we get the voltage, we can use the voltage for the 8 ohm, the voltage for this 8 ohm, because these two resistors do not divide the voltage. The voltage is the same. So if you're able to get a voltage, we use the voltage of the parallel section together with the resistance, and then we find the current. Now, how do we get the voltage? Is it possible we can do that? Let us check. One way is to find the total voltage of the voltage of this 3.6 ohm resistor, and also calculate the voltage of the internal resistor, which is the loss volt, and then we subtract it from the total voltage, which is the 14 volt, and then the remaining will be the voltage for this parallel section. But to be able to calculate the voltage here, we need the current, and the current is not known. Please let us be careful here. The current is no longer 1.4 amperes. The current has changed as a result of what? Opening another route for the current. So that new current is not known, which means that we cannot calculate the voltage of this and then the voltage of the internal resistance, and then we subtract them from 14 to get this voltage. So another method is to find the total current, that is the new current after we close this switch. The new current that will be read by this ammeter, and then when we get that new current, we see that these two resistors are current dividers. Then we try to divide it among the two, between the two resistors. So I think that can work because we know the resistance of the two. So let us proceed and then find the total current of the circuit. Now to do that, we need to use the EMF. We know the internal resistance. We calculated it in question 9.1.2, and then we know all the other resistors, so we can calculate the total current through that means. So we say 9.1.3, 9.2. First, we find the total parallel resistor by using the parallel formula. 1 over R parallel is equal to 1 over R1 plus 1 over R2, and then we substitute the 8 and the 6 ohm resistors, and then we get the parallel resistor. So with that one, we use the EMF formula, which is EMF is equal to the current times the total resistance of the circuit, and then the EMF is 14, which is equal to the current times the all resistors. Now all the resistance of the circuit is now what we substitute here. This is a parallel section, and then this is a 3.6 ohm, and then this is the internal circuit. And when we evaluate that with a calculator, we get the total current to be 1.88 amperes. As it's expected to be greater than 1.4, and that is what we have. Then we go back and then look at the two resistors. We divide the total current now between these two resistors. How do we divide it? Let us remember that resistance is inversely proportional to current. And what that means is that when we have a root of a high resistance, then that root is going to take low current, and then a root of low resistance will take high current. Now the total current that is coming from the ammeter is going to be divided into 14 equal portions. That is 8 plus 6 is 14. Then what it means that the root of low resistance will take eight portions of the total current, and then the root of a high resistance, which is this one, will take 6 portions of the total current. So to get the total current, or to get the current through the 8 ohms, that is going to be a lower current. It means that we have to use the proportion of this one, which is going to be a lower proportion, which is 6 divided by the 14 portions times the total. So that is a simple calculation, and then we say that current through the 8 ohm resistor is going to be 6 divided by 14 times the total current, which is 1.88, and then that gives us 0.81 amperes. So that is how to approach this question. There is another way that we can get, you can explore that. You can explore other ways of getting this current. That's the current through the 8 ohm resistor. Then we look at 9.3. A conducting wire of negligible resistance is now connected between points X and Y. Let's check what are points X and Y. This is point X, and then this one is point Y. So we can just look at how that would look like, and then okay, so we can take a wire from here, and then we connect the wire straight to X and Y. And then what are we going to see? Now this wire has a negligible or zero resistance. So what happens is that current always take a path of low resistance. So the current from the ammeter will no longer pass through this path, but it's going to pass through, because it's going to pass through the wire, and which means is that the 8 and then the 6 ohm resistors are not going to have current. In other words, we say that this portion of the circuit has been short circuited. This is short circuit. Then the current is taking that path. So we are going to see an increase in current. Whenever there is a short circuit, we see very large currents in the circuit. So the question says, what effect will it have on the temperature of the battery? Now we know that when current increases, current is associated with heat, or current produces heat, especially inside the battery. So the temperature is going to increase. And then what is the reason? The reason for the increase is that energy transfer to heat, especially inside the battery, increases. Electrical energy is converted to heat energy, and this makes the temperature of the battery to increase. And then this is the end of the solution.